Hello everyone, welcome to our channel Code with Sunny, and in this video we will be talking about the medium problem shortest unsorted continuous subarray. Its index is 581. Okay, so before moving further, let us look about the related topic section. You can see this problem is related to pointers, greedy, stack, sortings. Yes, okay. So you can also sort this, like you can also use sortings to solve this problem in and log in time. But basically in this video I will be focusing upon how we can solve it in O of n time complexity and O of 1 extra space. Okay, so let's begin. Given an integer array nums, we need to find one continuous subarray such that if we are able to sort this subarray in ascending order, then the entire array will be sorted in ascending order. Now we need to return the shortest such subarray and output its length. Okay, so basically we need to sort any subarray such that after sorting the subarray in ascending order, the entire array will be sorted in ascending order. So we will talk all about the examples. First, let's look over the constraints. You can see the max length of this array is going to be around 10 raised to the power 4. So O of n squared time complexity solution will not pass. So we need to focus upon O of n time or O of n log n time solution. So let's understand this problem with an example. So let's pick out one example: 2648264 8, and we have 10 9 15. 10 9 15. Now this is the input array, and we need to sort and sub array such that after sorting that sub array, the entire array would be sorted. Now if you focus over here, this sub array is the required sub array. Like if you sort this sub array, it would be like something 2 4 6 8 9 10 followed by 15. Now you can see this is the sorted array. So we are going to sort the array starting from this index and ending at this index. So our shortest length subarray is having the value 5. Okay, so how we are going to find out this value, this entire process efficiently? So the very first way is you need to sort this entire array. So when you sort this entire array, you have the array of this type. So you will find out the least index I such that there is a mismatch. So you can see the first index where there is a mismatch is this index 6 and 4. Okay, so this will be your starting end position, and you need to find the largest index such that there is a mismatch. So you can see this is the largest index such that there is a mismatch. So this will be your end position. So your answer would be E minus S plus 1. So yes, you can solve this in O of n log n time. So but I would be focusing upon how we can optimize our solution to O of n time complexity. Okay, so let's understand how this sorting criteria would help us. Okay, so I will take this same example. So it would be like 2 4 6 8 9 10 followed by 15. Okay, so what I will do, one more thing is like I will write down prefix maximum. So let it be denoted by PM, and also I will write down uh, SMI suffix minimum. So PMX will denote prefix maximum and SMI will denote suffix minimum. So I will say if PMX of 2, it means that I will consider first I plus 1 elements. Note that I am using a 0 based indexing. So 0 1 2. If I will say PMX of 2, you need to have the maximum. What is the maximum value over the all the elements from 0 to 2 both inclusive? Okay, so let's fill up the values of PMX and SMI. It would be like 2, 4, 6, 8, 9, 10, and 15. And similarly, SMI would be again 2, 4, 6, 8, 9, 10, 15. Now there is a one thing much interesting. You can see all the three arrays are actually same, right? So there is a one important property when the array is sorted in ascending order. You can see for every index I, like if I am at this position, the prefix maximum at this position up to the index I is always matching with the current value of the element. Similarly, suffix minimum of at the current position is always matching with the current value of the element, that is array of I. Okay, you can check at any index, like if you are at this index, you can see 9 is matching with this 9, and similarly this is also matching with this 9. Okay, so it gives us the idea that whenever we have a sorted array, then prefix maximum at every index must be matching with the array element value. Okay, now let's bring some twist. Okay, so let's erase some of the elements, like let's have the same array 2 6 4 8 10. So let me write down 2 6 4 8 10 4 8 10. Then we have the value 9, then we have the value 15. So let's write down PMX and SMI. PMX denotes prefix maximum up to the index I, and SMI will denote suffix minimum up to the index I. Okay, so let's write down the values of PMX and SMI. So it would be like 2, 6. Now again, the maximum of 6 and 4 is 6 again. 6 and 8 is 8. 8 and 10 is 10. 10 and 9 is again 10. 10 and 15 is 15. And similarly SMI suffix minimum 15 would come over here, then 9 would come over here, then minimum of 9 and 10 is again 9, minimum of 9 and 8 is 8, minimum of 8 and 4 is again 4, minimum of 4 and 6 is 4, minimum of 4 and 2 is 2. Okay, now as I've already said, when we have a sorted array, prefix maximum at every index must be equal to the array element value, right, at that position. Similarly, the similar case lies to the suffix minimum. So what I will do is, like, to find out the starting and end position, note that we must have to find this position and this position, which we need to sort this such that the entire array becomes sorted. Okay, so what we will do is like we will start traversing from the left hand side, and we will find out the end position such that end position will be the largest index I, such that the nums of I, which is the array of I value, is going to be strictly smaller than the prefix maximum value at that position. Okay, so let me write down the condition if you are getting confused. Nums of I is going to be strictly less than PMX at the position I. We need to find the largest index, and that index will correspond to the end position of the required subarray. Okay, so let's cross check it out. You can see 2 is okay, so 2, this value is not strictly less than 2, so this will not be our end position. Similarly, I will check for 6. So 6 is not strictly less than 6, so this will not be our end position. So 4 is strictly less than 6. This can be our end position. So in the process, E may be initialized with this value, but we need to check out some more values. So 8 is strictly less than 8. No. 10 is strictly less than 10. No. 9 is strictly less than 10. So here lies the case, like your end value, end position will be at this one, because the nums of I is strictly less than the prefix maximum of I. If we have a sorted array, then you can see nums of I must be exactly matching with the prefix maximum at this current position, current index. But here we have some arrays being rearranged. We need to find the starting and end position. So we will find out the largest index I, such that nums of I is strictly less than the prefix maximum of I, that will correspond to our end position of the required subarray. So can you guess how we are going to proceed with the finding of this start position? So this is quite much easy. So you will find the least index I, such that nums of I is going to be strictly greater than suffix minimum at that position I. Okay, so you will start iterating to this one. You can see you are going to have 15, 9, not, it is not less. Now you can see 10. 10 is not less than 9, sorry, 10 is greater than 9, so start may be initialized with at this position. Similarly, 8 is not greater than 10, 4 is not greater than 4, 6 is strictly greater than 4, you can see. So start position will automatically will be initialized with this value. So yeah, here lies the case, start and end. So our answer is end minus start plus 1. Note that we can use a single variable to keep track of prefix maximum and suffix minimum. Right, so let's look out the code how we can implement that efficiently. Okay, so you can see n is num size, start is initialized with -1 and end is initialized with -2. Note that if the entire array is already sorted, so end minus start plus 1 will be automatically 0 if you calculate this value. That's why I've taken start as -1 and end as -2. And minimum will be int max initialized with int max and maximum will be initialized with int minimum. Note that we will keep track of minimum from the suffix side and maximum from the prefix side. So I will start from the prefix side first. So we will use the mx variable. So each time we will first calculate the prefix maximum, and if our current value array value is strictly less than the prefix maximum, so this can be our end position. So we will initialize with end as I, like assign end as I. Note that we need to find the largest index I such that this criteria will hold. So that's why every time when we have nums of I strictly less than mx, we will assign end as I. Similarly, we are going to do that from the suffix side such that the you can see we are going to use a minimum case like mn variable and minimum we are using each time, and whenever we have nums of I strictly greater than minimum, this can be our start position. Since we need to find the least index I, we will assign start as I each time when this if criteria holds true. And finally our answer is end minus start plus 1, which is the required subarray starting from start to end both inclusive. So if you guys have still any doubts, you can reach out to us through the comment section of the video, and thank you for watching this video.